Welcome to the deep dive. Today, we're strapping on our hiking boots and heading into the breathtaking world of mountains. We've got some incredible slides and research ready to guide our ascent. So, get ready to explore the powerful forces that build these majestic landforms, how we categorize them, and the surprising impact mountains have on the planet.
It's easy to think of mountains as these permanent fixtures, but they're actually incredibly dynamic. They're constantly evolving, shaped by forces that have been at work for millions, even billions of years.
Okay, so let's start with the basics. We all have a picture in our minds when we think of a mountain, but how do we actually define them?
Well, at their core, mountains are large landforms that rise significantly above their surroundings. That might seem obvious. But it's important to note that it's not just about height. It's about that dramatic rise from the surrounding landscape. Think about it like this. A plateau might be high, but it's relatively flat. A mountain, on the other hand, has that distinct peak or series of peaks that really set it apart.
That makes sense. So, how do these dramatic peaks come to be?
They're formed through a fascinating interplay of forces. Some are born from the fiery depths of the earth, built up by volcanic eruptions. Others are sculpted over millennia by the relentless forces of weathering and erosion. But the real heavyweights of mountain building are tectonic forces.
Tectonic forces, those are the ones that move the continents around.
Right, exactly. Imagine the Earth's crust as a giant jigsaw puzzle, with massive plates constantly shifting and bumping into each other. These plates, driven by the heat from deep within the Earth, are constantly on the move. And where they collide, buckle, and grind against each other, mountains rise.
So those collisions are like the ultimate mountain-making machines.
Precisely. We call this process orogeny, and it's responsible for some of the most awe-inspiring mountain ranges on Earth. Take the Himalayas, for example. They were formed over millions of years as the Indian plate collided with the Eurasian plate, pushing up the land into those towering peaks.
It's mind-blowing to think about those forces at work right beneath our feet.
It really is. And orogeny isn't just about pushing land upwards. It also involves folding, faulting, and the transformation of existing rocks under intense heat and pressure. It's a complex, dynamic process that unfolds over vast stretches of time.
So it's not just a quick makeover. It's like a slow-motion ballet of geological forces.
Exactly. And these tectonic plates don't just collide randomly. There's a system to their movements. We categorize their interactions into three main types of boundaries: convergent, divergent, and transform.
Okay, let's break those down. What's happening at a convergent boundary?
That's where things get really interesting. Convergent boundaries are where plates collide head-on. It's like a clash of titans, and mountains are often the dramatic result.
When two plates collide, one has to give way.
Right.
Got it.
Context. One plate will slide beneath the other in a process called subduction. This often happens when a denser oceanic plate meets a lighter continental plate. The oceanic plate dives down into the mantle, and that process generates immense heat and pressure, melting rock and fueling volcanic activity.
So, volcanic eruptions are a byproduct of these plate collisions.
Exactly. And those eruptions can build up some impressive mountains over time. Think of the Andes Mountains in South America, a chain of volcanic peaks that stretches for thousands of miles.
Wow, that's incredible. What happens when two continental plates collide?
Well, they're both too buoyant to subduct, so they end up buckling, folding, and thickening, pushing the land upwards. The Himalayas, home to Mount Everest, are the ultimate example of this type of collision.
The highest mountain range on Earth was formed by two continents essentially crumpling into each other.
That's right. It's a testament to the incredible power of these tectonic forces. And those collisions continue to shape the Himalayas to this day, pushing the mountains a little higher each year.
I never realized the Himalayas are still growing. What about those other plate boundaries, the divergent and transform ones?
Well, divergent boundaries are where plates move apart, allowing magma to rise and create new crust. It's a process of creation rather than destruction.
It's like the Earth is splitting open and birthing new land.
You could say that. Think of the Mid-Atlantic Ridge, an underwater mountain range that snakes down the middle of the Atlantic Ocean. It's constantly growing as new crust forms at this divergent boundary.
That's amazing. And what about transform boundaries?
Those are where plates slide past each other horizontally. It's a bit like rubbing two bricks together, creating a lot of friction and tension.
That sounds like it would make for some shaky ground.
It does. The San Andreas Fault in California is a prime example of a transform boundary. It's notorious for its earthquake activity, as the Pacific plate grinds against the North American plate.
Okay, so we've got these different types of plate interactions, all capable of creating mountains. But let's zoom in on orogeny, that mountain building process and look at the specific ways it unfolds.
Absolutely. We can break down orogeny into three main types: thrust orogeny, collisional orogeny, and accretionary orogeny.
Okay, I'm intrigued. Let's start with thrust orogeny. What's happening there?
Think of it like pushing a rug against a wall. The rug buckles and folds, creating ripples. Thrust orogeny works in a similar way. It happens at convergent boundaries where one plate is forced under another. That powerful collision creates intense pressure, causing layers of rock to buckle and fold, pushing them upwards to form what we call fold mountains.
Those classic mountain ranges with those wave-like folds are formed by this thrusting action.
Exactly. The Appalachian Mountains in eastern North America are a great example of fold mountains formed by thrust orogeny.
And what about collisional orogeny? Is that just a more intense version of thrust orogeny?
It is more intense. Collisional orogeny happens when two continents collide head-on. There's nowhere for either plate to go, so they end up crumpling, thickening, and uplifting, creating vast, towering mountain ranges. The Himalayas, once again, are the poster child for collisional orogeny.
It's like those two continents are engaged in an epic slow-motion wrestling match, and the mountains are the result.
That's a great analogy. And finally, we have accretionary orogeny. It's a bit more like building a mountain range piece by piece.
Okay, how does that work?
Imagine smaller fragments of crust, called terrains, colliding and attaching to continental margins. It's a gradual process, a bit like adding pieces to a puzzle over millions of years, building up complex mountain belts. The Pacific Northwest of North America is a good example of a region shaped by accretionary orogeny.
So, mountains can be formed by these smaller bits of crust glomming onto existing continents.
Precisely. It's a fascinating reminder of how dynamic and constantly evolving the Earth's crust truly is.
It's incredible to think about all these forces at work, shaping the landscape over millions of years. But there's another key process we need to discuss: uplift.
Ah, yes. Uplift is the vertical elevation of the Earth's surface, and it's a crucial element of mountain building. Think of it like this. You've got these tectonic forces pushing and squeezing the Earth's crust, but you also need that upward force to create those towering peaks.
It's not just about folding and faulting, it's also about that vertical push.
Exactly. Uplift is driven by several factors, including those plate boundaries we discussed, but also things like mantle plumes, which are upwellings of hot rock from deep within the Earth, and isostasy.
Isostasy, now that's a new one.
Think of it like this. The Earth's crust is a bit like a giant raft floating on the denser mantle. When you add weight to one part of the raft, it sinks a bit lower, and when you remove weight, it rises. Isostasy is the process of the Earth's crust adjusting to maintain that balance. So, when you have mountain building going on, the added weight of those mountains causes the crust to sink a bit, but at the same time, isostasy is working to push the crust back up, contributing to the uplift of those mountains.
It's like a constant balancing act between the weight of the mountains and the buoyancy of the Earth's crust.
Exactly. And we can actually measure this uplift using sophisticated tools like GPS and satellite imagery. We can track those subtle movements of the Earth's crust over time.
We can actually see mountains growing, even
Right.
if it's at a snail's pace.
Yes. And that uplift has ripple effects. It affects drainage patterns, creating new rivers and valleys. And it influences the development of ecosystems. Imagine the challenges of building roads and infrastructure in a region undergoing uplift.
It's a reminder that Earth is a dynamic, constantly changing system. And speaking of those challenges, let's shift gears and delve into the different types of mountains we see across the globe, each with its own unique formation story. We'll start with tectonic mountains, those born from the forces of plate tectonics.
Great idea. Let's unpack the mountain menagerie. Starting with the most common type, fold mountains.
Fold mountains, those are the ones that come to mind when you picture those classic
Right.
wave-like folds.
Exactly. Fold mountains are created by compressional forces at convergent plate boundaries. As those plates collide, layers of rock buckle and fold, creating those characteristic upfolds called anticlines and downfolds called synclines.
It's like seeing the Earth's wrinkles up close. I've always been fascinated by how those folds create such dramatic landscapes.
They're truly spectacular. The Jura Mountains in Europe and the Zagros Mountains in Iran are stunning examples of fold mountains.
And what about fault block mountains? Do those involve a bit more fracturing?
They do. Fault block mountains are formed by uplift and tilting along faults. Those breaks in the Earth's crust. Imagine blocks of crust being raised or lowered, creating a landscape of dramatic peaks and valleys.
Sayings like the Earth's crust is cracking and shifting,
Yeah.
creating those peaks and valleys.
Exactly. The Basin and Range Province in the western United States is a classic example of fault block mountain terrain.
And then we have upwarped mountains. Are those the more gentle giants of the mountain world?
You could say that. Upwarped mountains are characterized by broad uplifts with relatively gentle slopes. They're often associated with the doming of the Earth's crust, where magma pushes upward from below, creating a broad, rounded uplift.
So it's like the Earth is being pushed up from below, creating a giant dome.
Precisely. The Black Hills of South Dakota are a beautiful example of an upwarped mountain range.
Okay, so we've explored mountains formed by the intense forces of plate tectonics. But what about volcanic mountains? Those fiery architects of the landscape deserve their own spotlight.
Absolutely. Volcanic mountains are built by the accumulation of lava and ash erupted from volcanoes. It's a process that can create a wide variety of shapes and sizes, from gently sloping shield volcanoes to towering composite volcanoes.
Let's dive into those different types of volcanic mountains. What are some of the key characteristics that set them apart?
Well, shield volcanoes are like the gentle giants of the volcano world. They're built by eruptions of fluid basaltic lava, which flows easily and spreads out over large distances. This creates those broad, gently sloping cones that resemble a warrior's shield lying on the ground.
They sound almost peaceful compared to those explosive eruptions you see in movies.
They can be quite impressive, but their eruptions tend to be less violent than some other types of volcanoes. Think of Mauna Loa in Hawaii, the largest volcano on Earth. It's a classic shield volcano.
So those iconic Hawaiian volcanoes with their flowing lava and relatively calm eruptions are shield volcanoes.
Exactly. Now, on the other end of the spectrum, we have lava domes. These are formed by viscous lava that doesn't flow easily. Instead, it piles up around the vent, creating a bulbous mound.
So it's like the lava is too thick and sticky to spread out, so it just builds up in a dome shape.
Precisely, lava domes tend to be much smaller than shield volcanoes, and they can be quite dangerous because the pressure can build up inside, leading to explosive eruptions.
It sounds a bit more like those dramatic eruptions we see in movies.
They can be quite explosive. And then we have cinder cones, which are built by explosive eruptions of tephra, those fragments of volcanic rock and ash. These eruptions create steep-sided cones that often form in groups.
So it's like the volcano is spitting out bits of rock and ash, and those fragments build up into a cone shape.
You got it. Cinder cones are typically smaller than other types of volcanoes, and their eruptions tend to be relatively short-lived.
And finally, we have composite volcanoes. Are those the ones we typically picture when we think of a volcano?
They are the most common type, and they often create those iconic symmetrical cones. They're called composite volcanoes because they're built up by alternating layers of lava and tephra.
So they're like a layered cake of volcanic materials.
That's a great way to picture it. And those layers reflect the volcano's history of eruptions with periods of lava flows followed by explosive eruptions of ash and rock.
And those composite volcanoes can be pretty impressive in size, right?
They can be massive. Think of Mount Fuji in Japan or Mount Rainier in Washington State. Those are classic examples of composite volcanoes.
Okay, so we've covered mountains formed by tectonic forces and those built by volcanic eruptions. But what about mountains that are sculpted by the relentless forces of weathering and erosion?
Ah, yes. Erosional mountains, those shaped by wind-water ice and even plant roots working over millions of years to carve away at the landscape. They might not have the dramatic origins of tectonic or volcanic mountains, but they're just as fascinating.
They're like works of art sculpted by nature itself.
Exactly. And their formation is all about the interplay of weathering, the breakdown of rocks, and erosion, the transport of that weathered material.
So it's not just about building up, it's also about breaking down.
Absolutely. Weathering and erosion work together in a continuous cycle, shaping the landscape over time. Think of wind and rain wearing away at rock faces, glaciers, carving out valleys and rivers, carrying sediment downstream.
It's incredible to think that even the mightiest mountains are subject to these constant forces of change. What are some of the most distinctive features created by erosion?
One striking example is a cirque, a bowl-shaped depression carved by glacial erosion. Imagine a glacier, that massive river of ice, slowly grinding away at a mountainside, creating this dramatic amphitheater-like feature. They often hold picturesque alpine lakes, adding to their beauty.
So those pristine alpine lakes nestled in the mountains are often the result of glacial erosion.
Many of them are. And then we have buttes, those isolated hills with steep sides and flat tops formed by weathering and erosion. They often stand out as solitary sentinels in arid landscapes, a testament to the power of erosion to shape the
And
land.
they do have a certain majestic quality to them.
They do. And speaking of majestic, we can't forget mesas, those elevated areas of flatland with steep sides. They often look like giant tabletops, and they're also shaped by weathering and erosion. They're often capped with a harder layer of rock protecting the softer layers beneath from erosion,
Yeah.
which is why they have that distinctive flat top.
So it's like the harder rock is acting like a shield, preserving that flat top.
Exactly. And finally, we have plateaus, those vast elevated areas of relatively flat land. They can be formed by uplift volcanic activity or the erosion of surrounding areas. They're often cut by deep canyons and valleys, creating some of the most dramatic landscapes on Earth.
The Grand Canyon is a prime example of a plateau shaped by erosion, right?
It is. The Colorado River has been carving its way through the Colorado Plateau for millions of years, creating that awe-inspiring canyon.
It's a powerful reminder of the immense power of erosion to shape the Earth's surface. We've explored the incredible forces that build mountains, the different types of mountains that exist, and the processes that sculpt them over time. But mountains are more than just geological wonders, aren't they? They play a vital role in our planet's ecosystems.
They do. Mountains are like the planet's water towers, its climate regulators, and its biodiversity hotspots. They're essential to the health of our planet and the well-being of countless species, including our own.
Okay, let's delve into those roles. How do mountains influence our planet's climate?
Well, one of the most significant ways is through a phenomenon called the rain-shadowed effect. Imagine a mountain range standing in the path of prevailing winds as moist air is forced to rise over those mountains. It cools, and the moisture condenses, releasing precipitation on the windward side. This creates a lush green environment on one side of the mountains.
So you get a lot of rainfall on the side of the mountain range that's facing the wind.
Exactly. But as the air descends on the leeward side, it's drier, creating a rain shadow effect. This often results in arid or desert-like conditions on the other side of the mountains.
So you can have two completely different climates on opposite sides of a mountain range, all because of this rain shadow effect.
That's right. And mountains also influence climate through temperature variations. As you go higher in elevation, the temperature drops. This creates distinct climate zones, from lush forests at lower elevations to alpine tundra and glaciers at higher altitudes.
It's amazing how a single mountain range can create such a diverse range of environments. And that diversity of environments leads to biodiversity, right? We often hear about mountains being biodiversity hotspots.
Absolutely. Mountains provide a wide range of habitats, supporting an incredible array of plant and animal species, many of which are found nowhere else on Earth.
So they're like islands of life, each with its unique collection of species.
Precisely. And not only do mountains support high levels of biodiversity, but they also act as natural barriers, separating populations of plants and animals and influencing their distribution and evolution.
So they're not just static landforms, they're dynamic ecosystems, constantly shaping the life around them.
Exactly. And we can't forget about water mountains are often called the water towers of the world.
I've heard that term before, but I'm not sure I fully understand what it means.
Well, think about it this way. Snow and ice accumulate at higher elevations, and as they melt, they release water that feeds rivers and replenishes groundwater, sustaining downstream ecosystems and human populations.
So mountains are like nature's reservoirs, slowly releasing water throughout the year.
Precisely. And the geological processes in mountains like weathering and erosion also influence soil formation and nutrient cycling, further impacting the health of ecosystems. It's a complex web of interconnected processes, and mountains are right at the heart of it all.
It's incredible to think of these towering peaks playing such a vital role in the delicate balance of our planet's systems. And it makes me wonder about the impact we as humans are having on these majestic landscapes.
That's an important question to consider.
We're drawn to their beauty, we challenge ourselves to climb them, and we rely on them for resources, but our activities can also have a significant impact on these fragile ecosystems.
Absolutely. Climate change, for example, is already having a visible impact on mountain environments, from melting glaciers and altered precipitation patterns to shifts in plant and animal communities. It's a pressing issue that demands our attention.
It's a call to action, not just to protect these incredible landscapes, but to understand our role within them.
I couldn't agree more. Mountains have inspired awe and wonder in humans for centuries. They're woven into our cultures, our myths, and our art, but they're also vital to our survival and well-being.
So as we wrap up our deep dive into the world of mountains, what's the key takeaway you hope our listener will carry with them?
I hope they'll come away with a deeper appreciation for the dynamic forces that shape our planet, the interconnectedness of Earth's systems, and the crucial role that mountains play in our lives.
It's easy to take them for granted, but there's so much more than just static backdrops to our lives. They're living, breathing ecosystems that deserve our respect and protection.
And maybe even a bit of our wonder and awe as well.
You know, as we've been talking, I keep thinking back to those incredible slides we saw. Those visuals really brought these geological processes to life, didn't they?
They did. Visualizing these complex concepts can make a huge difference in understanding. It's like taking a virtual field trip through millions of years of Earth's history.
Exactly. It highlights the beauty and power of scientific inquiry. By studying these processes, we gain a deeper understanding of our planet and our place within it, and that understanding can inspire us to be better stewards of these incredible landscapes. It really makes you realize just how much we depend on mountains, not just for their beauty, but for the essential resources and services they provide.
It's a powerful reminder of our interconnectedness with the natural world.
Absolutely. So for our listeners who are feeling inspired to learn more and perhaps even explore some of these mountain ranges firsthand, what resources would you recommend?
Well, for a deeper dive into the science of mountain formation, I'd recommend John McPhee's Annals of the Former World. It's a Pulitzer Prize-winning masterpiece that explores the geology of North America through the lens of its mountain ranges.
And for those who are more visually inclined, the BBC's Planet Earth series has some breathtaking footage of mountain ranges from around the world.
That's a great one, and of course, for those who want to experience the majesty of mountains firsthand, I highly recommend visiting our national parks. Many of them are home to stunning mountain ranges, and the Park Service websites are a wealth of information on the geology, ecology, and history of these areas.
Fantastic recommendations. We'll include links to those resources in the show notes for our listeners.
Perfect. And I would just encourage everyone to get out there and explore, whether it's a hike in your local foothills or a trek to the Himalayas. There's something truly awe-inspiring about experiencing the power and beauty of mountains firsthand.
Well said. As we wrap up our deep dive into the world of mountains, I'm left with a renewed sense of wonder about these majestic landforms. They're not just static backdrops. They're dynamic ecosystems constantly evolving and shaping the world around them.
And they're a powerful reminder of the incredible forces that have shaped our planet over billions of years.
We've scaled some serious knowledge peaks today, exploring the forces that build mountains, the different types that exist, and the crucial role they play in our planet's ecosystems.
And hopefully we've inspired our listeners to continue exploring and learning about these incredible landscapes.
And as a final thought-provoking question for our listeners to ponder, we'd like to leave you with this. How do you think mountain ranges have influenced the course of human history and the development of civilizations?
It's a question that invites us to consider the profound and often overlooked connections between humans and the natural world.
So until next time, keep exploring, keep learning, and keep those mountain peaks in your sights.